Yes. Yeah. Yes. ছবি না হলে ছবি দেখতে পাবো নিচটাতে ইউটিউবের নিচটাতে ছবি দেখতে পাবো তারপর ছবি আসছে না এটা সরিয়ে দিয়েছে না না ক্যামেরাটাকে তুলে দিয়েছে যেটা মুখটা বড় হলো সাইড স্লাইডে চলে যাই সাউন্ডটা ওনাটা যে সাউন্ড এইটা বোধহয় সরিয়ে দিতে হবে ঠিক আছে
Am I audible? Maybe thoda tough. Less. But this is minimum. All right. This is too loud. All right. Right. Yes. This is better. Good morning. Yes. So I just want to know how many of you have already used HPC, introduced to HPC. You are using. Okay. So the majority of you have never used or not got introduced to HPC. So I will try to keep it start from very basics and tell you about what HPC is, how does it work, and a few other things regarding. So this is my talk outline. Do you want to check if it's somebody is watching from outside the slide stage? Yeah. Okay. Alright. That's good. So I will begin with an introduction. Then we will talk about the basics of HPC, and then we will see how supercomputer. What are the components in a supercomputer? And this will help you in understanding what we have in the Param Shakti. And then we will see how parallelism, which is the basics things that HPC needs, how it is in architecture and how is it's done in the software, and then we will end up with the summary. My request to you would be that whenever there is a class which is a theory, pay attention to the teacher. If you are using your laptop, you are causing two harms. You are diverting the attention of your neighbor towards what you are doing, and you are not giving. I mean, you are also the teacher also gets irritated because the student who is sitting in the class and not listening to him is not a good for the teacher. So always remember this, not for this class, but when you are hands-on, then you are free to use your laptops. So please refrain from using laptops when you are listening to somebody who is delivering the lecture. All right. So let's begin. So with the introduction. So we'll begin with basics of computing as stated by two professors, Norman Gibbs and Alan Tucker. And this is what was in fact mentioned. The same thing was mentioned by Professor Chakravarti, that you should get to the basics of things. So getting to basics of things is very important because only when the basics are clear, you can build upon that. So he said that, I mean, they have said that algorithms. So algorithm is the basis of computing, any computing, and they are designed and they are developed to solve a large number of problems. I mean, even from your day-to-day life, you have algorithm, like what you should be doing today. Like you would have been given the agenda, then you have to get ready, come here, all that. So there is a what is algorithm a step-by-step process. So they are for solving a problem. The first thing, like many of you here would be research scholars. So the algorithms are designed for solving a large different range of problems. And first, when you design an algorithm or think of an algorithm, especially mathematical algorithms, you have to first see whether about their correctness. That is your first thing. And even in supercomputers or even in computing, whatever you do, the correctness is important. So you would have known that there is something like test data and there are test results, and you validate whatever you do with this test data and test results to make sure that what you are doing is correct. That is the first thing that you have to see. Whichever computers you use, whatever algorithms you use, you will always look for correctness. And you would have known that there were some bugs in some of the processors, and if there are bugs in processor, they have to be thrown away. So when you look for that, first is correctness, and once you have a correct algorithm, then you will look for efficiency. Meaning how fast you can do it, how better you can do it. Efficiency is not just related to time. It could be, excuse me, please put this down. Okay, so pay attention here. If you have anything to talk to him, finish it off. Don't disturb. So I was saying that efficiency refers to time, how fast you can do it. Efficiency can also refer to how much space it is taking, the program is taking, how much intermediate space for data you need. So efficiency refers to too many things. Okay, so you can optimize it for one of those parameters, time, space, whatever. Okay. So that is the second thing. Whatever algorithm you work on, first once you get it right, then you have to see how it can be made efficient, particularly when you are running it on a computer. Then once, see, these algorithms and maths that came even before computers. The word algorithm, maybe you can Google it out and you will find that it was named after a Persian mathematician, Muhammad al something. Okay. Huh? Correct. Right. So that algorithm and al comes from there. So he built upon the mathematics that Indians had proposed, in fact. And he proposed these things, which means on in whose honor the word algorithm comes. So once you have the algorithm, which he did in the 8th and 9th century, and computers came just 75 years ago, as I shall tell you later. So now we are moving from the algorithm part to the computation. So these computers that we build are meant to execute these algorithms. Some of these computers, most of it, what we use are general purpose, like Param Shakti. We can execute a variety of algorithms. However, there could be certain computers which are specially designed to execute certain algorithms. Like there are few, one made by a DB Shaw and company. So they are meant for executing only molecular dynamics programs. So they are custom built. So you could have a variety of them, or you would have seen these days that many of the CPUs, they come with tensor cores which are specifically optimized for running the algorithms related to AI. These days they are coming in the phones, the CPUs that are used, Snapdragon CPUs that are used in your phones, because increasingly we are using AI-related algorithms in our day-to-day lives. So the purpose of computers, as in a crude way, you can say that they are supposed to execute algorithms. So now computers cannot understand algorithms. They are not like sound operated and they say that this is my algorithm and execute it. Somebody has to tell them, because computers are dumb. They will run the code that you put on them. So to convert the algorithm into what the computers can do, you need programming languages. And that's why you have different types of programming languages. Simple like C, and then there is R, and there are so many Java. Each one is suited for doing certain type of tasks, or each one is suited to convert certain types of ideas that human beings have into the way the computers can understand. Like if humans understand objects, for certain purpose, then you have object-oriented program. If you want to do statistics and inferences, R probably is the language. Similarly, you are in your languages coming, and there are books written on what are the functional languages, this, that. So I will not get into that. So that is, but the crux lies in translating the ideas of algorithm into something that computers can understand, which are programs, unit programming languages. And finally, these programs are executed by the computer systems. Then you have compilers, because computers understand machine language. Humans cannot write in machine language, so you have higher level languages and the compilers, linker, loaders, you all know. And finally, once you have this setup, that starting from algorithms to computers that can execute these algorithms, the next step is to identify the problems. Like we have here students, research scholars from various domains. She is from ocean engineering. So she is concerned about currents in the ocean and how the precipitation affects possibly the weather, where will it rain in India based on the conditions, maybe El Nino she is also studying. Right? So we have to identify the problems that can take advantage of computer systems, then convert the problem statement into algorithm, and then take it to the computers. Okay. So that is where you have two types of, I will mention that again later. To make this happen, you need two types of people, two types of human resources. One which understands the physics, chemistry, maths behind this, and the computing experts who understand how a particular algorithm can best fitted on a given computing system. Like traditionally, we had purely CPU based systems, and as I shall tell you later, the increasing power of the computer was derived by adding more and more CPUs. But there came a time when we started using GPUs because they were good at doing certain things. And today we have a hybrid architecture. Like Param Shakti that you have here has got CPU based nodes and certain nodes which have got GPUs in it. And there are certain algorithms, as I shall tell you later, which can take advantage of those GPUs. So the computational experts will then translate the algorithms that the domain experts have developed into how best can be executed on a given computing system. Or they can recommend that, hey, we want this kind of features in the hardware that you have. So that is the most important thing. Finally, humanity wants that certain important problems, like how best can we predict the weather over Kharagpur. At the moment, we may not be able to do it. You always say that, oh, I went to US and they said that tomorrow it will rain at 3 o'clock, and it actually rained at 3 o'clock. There is a difference between the way it's predicted in that part of the world and this part of the world. The algorithms are same. WRF is the code. So we have to think about how what we can do to make sure that we we solve the problems that face the humanity. And as I shall tell you later, finding vaccine for COVID, HPC was used extensively. Many of the common people will not know about it, but that's the way it works. So these are some problems. There are some, as they are called as grand challenge problems for supercomputers. And similarly, there are other problems which are used by other computing systems. So we have to identify them and solve them. However, there is a bit of caution that it is not possible to solve every problem algorithm. There is also a limitation. It's not that algorithm is a medicine that is available for every problem that we have. So whenever we look at the positive things of something like an algorithm, we should also look at the limitations of that. And that is where you can, there is a big page on this gentleman as well. So was this German logician Kurt Gödel, and even before computers came in the 1930s, he proved that there are some problems for which no generalized algorithm can give a solution, and he called them as unsolvable problems. So there is a Scientific American article also on this, what are unsolvable problems, and there are some examples that are given. I will not get into that for paucity of time, but this also should be remembered that there are some things and other while there are theoretically some problems for which there does not exist a solution, it is also possible that, as I shall mention later, there are some problems for which today we don't have an algorithm. But young minds like you, they can come up with algorithms that can, which were treated as non-solvable. Get to know this. Somebody gets a Turing Award or ACM Award for finding an algorithm which was earlier inefficient or earlier unsolvable. So that's a whole lot of science that goes behind algorithms, and that anyway not part of my discussion. Okay. And other variety of algorithms is there are algorithms for which the computers can run them, but they will take too long to be made practical. Like you can theoretically calculate that if a computer algorithm is designed to use brute force method to play chess, like one step, what are the possible, when the other person makes his move, what are the possible moves that are possible? Then you keep multiplying. The other person can take one of those moves, then just keep multiplying. It will become so long that maybe computers of today may take years if you are using a brute force method. But of course, there are some algorithms wherein you try to reduce those moves by saying that this is not possible and all. However, point being made is there are many algorithms which are solvable, but it is impractical to use computers to solve them because they are going to take very long time. And many of these things, like trying to know what is tomorrow's weather, you want the answer by evening. You don't, if the answer comes after 3 days, you can only say that, hey, what I predicted was right or not right. So time is also a criteria in deciding about the solvability or non-solvability of a practicality, I would rather say, of that algorithm. And as I mentioned, there are some problems which today we feel are not solved. We don't have the algorithm to solve them. We know the problem. We know what is to be done, what is the solution we want from that. But how to reach that solution, we do not know. And so what we don't know is what is the step-by-step way of solving that problem. Hence, discovering an algorithmic solution, what I mentioned, has got a significant consequence. So people are working on problems, they are trying to find an algorithm to solve them. Once they find it, they can use computer, that is the aim. And there are some problems for which solution or algorithm do not exist today. So these are one of the research areas that many of the research scholars tries to. So I hope this forms the basis, what I described in these 2 slides, that forms the basis for our desire to use HPC for this purpose. Okay. So this one is the first computer that was made, called as ENIAC, and it was made exactly 75 years ago, and that was built for US Army. And the purpose was in the field they had these artillery guns, and these artillery guns were supposed to launch, send those ammunition inside, put inside that to the destination where the opposition army was. Now, how to calculate the angle of that. For that, they created a firing tables. Like this is the bit speed. These are some conditions. So these are like logarithmic tables that you have. Similarly, you could calculate that and give it to the soldiers. They would see what are the parameters and find the value and set the angle. But by the time it was made, the World War II got over, and it was made. As a result, it was used to study the feasibility of a thermonuclear weapon. So that rest of it is history. You might have seen the movie or it. But as you can see here, there are these wires through which it was programmed. So it was programmable in the sense that it could be told what is to be done, the algorithm to be followed, but the programming is one to a set of wires. So subsequently, von Neumann came in and he proposed the von Neumann architecture, and rest is a history. So this computer that he had is, as you can see here, this is a green line, and this green line indicates OPS, that is operations per second. Could do modest, something like 10 to the power 1 or so, or 10 to the power 2 operations in a second. So when we say operations, they refer to integer operations. However, here you see here that it went on, the computers that we had, which were electromechanical, based on vacuum tubes and relays and other things, they kept doing better and better integer operations per second. Subsequently, we started getting computers which could do floating point operations. So I am sure you know the difference between fixed point, that is integer, which has limited capability in terms of accuracy, and floating point operations are much more accurate. Can anybody tell me what happened in this time which made the computers do maths in a better way? Yes, the transistor was invented. And once transistor was invented, we started getting gates which were based on semiconductor. So instead of the logic being implemented using relays or vacuum tubes, we started doing it using semiconductors, and that's how their capability increased manifold. And as this graph, if you follow it, you find that today we have things which are 1 into 10 to the power 18. I think it might not have reached here exactly, but today we have an exascale supercomputer, which I shall tell later. Okay? So this is how the things have progressed, and today supercomputers' power is measured in floating point operations it can do. Okay? So this clock, what is this unit? So as I mentioned, it is the number of floating point operations one can do in a second. So all these terms are used interchangeably, but it is floating point operations per second. And you have gigaflop, teraflop, petaflop, and today the fastest computer can do 10 raised to 18 floating point operations in a second. So this is what is called as there is something called as a theoretical peak, means the maximum capability that it has. However, the usable capacity, how does it perform while running a practical code, that is done using what is called as a program called LinPack, high performance LinPack. So this mimics real life algorithms, like you have CFD codes, you have bioinformatics code, you have computational mechanics code. So the algorithms in that, they are packed into this HPL, and what is the real life performance it can give. So that is done through this, and you can visit this site top500.org later, and that will give you which are the world's top 500 supercomputer as of date. So this list is published twice a year. In November it will be published. Now 2 weeks time it will be published, and it's published in June next year. So every year, June and November, this list is published. Yeah. About HPL?
Yes, it is HPL.
Okay. So as this name suggests, there is a program called as LinPack. So what it has is, it has got some mathematical computation. It is computation intensive. It works on large amount of data, and for any grand challenge problems that I will describe in the slides to come, which are fit for to be used on a supercomputer, there are some core kernels. Like a CFD will have, maybe Shobnath will tell you what are the core kernels in that. Or if you are running a WRF code which is used for weather forecasting, there is something called as calculation of Lagrange's polynomial. That has to be done very frequently. So what we do is, there are some, if you like one of the things maybe I will mention later is typically what we do is we think serially. Our mind works serially, but computers have these supercomputers have been programmed with algorithms which are parallel in nature. So, and many of the serial algorithms exist. You have to see the parallelism in that and convert it into a parallel code. So there are programs that identify which part of your code or which section of your code is taking longest time that it can analyze. So when you analyze that, these are the ones which should be parallelized, and these are the ones which will give you a performance increase. Because let's say a program takes unit amount of time to run in a serial mode. 0.6 of that is spent in just one module or one subroutine. Then if you attack that subroutine, and instead of it taking 60% of the time, if you bring it down to 10%, so 10 plus 40, so your time will come down to half. But you should not concentrate on the remaining 40%, because it's not going to have as much effect as this one small routine will have. And most likely the remaining 40% anyway cannot be parallelized, because it's actually a serial code, non-parallelizable. So such things are taken, and there is one person by name Jack Dongara, and there are two more professors. They together worked out this, and for the past 25 years we have been using the same code to rate. So top 500, the list is made using the, so once you run it, you can tune it to your architecture, and once you run it, it may run for 1 day, 2 days, 3 days, depending on how big the computing system is. And at the end of it, it gives one output file saying that this it used the matrices of this size, it did this, these were the starting conditions, and finally it could extract 1.1 example of compute power out of this. Actual theoretical maybe 1.5, 1.6, but what it could achieve was 1.1. Like that, it gives a final result. So these results have to be submitted. Suppose we build Param Shakti here now. We will run this code and we will submit the results to them. Then they will see whether it fits in the top 500 and include. That is the way to use it. So this is the graph that shows how things have progressed. And you can see here, this one, the triangles are the number one system, and the squares are the 500 times. So you draw a vertical line, let's say 1995, the lines are not visible here. So you will find that in 1995, the top supercomputer was 100 gigaflops, that is 100 into 10 to the power 9 floating point operation, and the one that was at the entry was 1 gigaflop. So here the range is 1 gigaflop to 100 gigaflop. If you go here, the range could be 100 teraflops to 10 petaflops. Like this, it gives you a, and this is the sum, so we can ignore this. That's a cumulative power of top 5. So one of the things that you can see here, that there is a horizontally, they are the same systems. That means no new system came which was powerful for them between the year 2003 and 2005. Or here for the 6 times, 6 lists, the same supercomputer remained at number 1. Though this more and more came in here and it started. Another point to be noted here is, if you draw a horizontal line like this, what it tells us, the supercomputer which was the number 1 in 1994 became the 500th in, let's say, 2003, and in 2004 it was not one of the top 500 supercomputers. Which means that today the mobile phone that you have in your pocket has got much more compute power than the top supercomputer maybe 10 years ago or 15 years. Because whatever good things are happening, optimizations, efficiency, more compute power for these systems finally get reflected into the desktop CPUs, the mobile phone CPUs, to laptop CPUs. So this is a moving target. Top supercomputer in the world is a moving target, or the top 500 supercomputers in the world is a moving target. So the one that is present today is has got 1.1 exaflop. This was the one we officially recognized as the first exaflop system in the world. And what happens is there are many supercomputers which are privately held or held by defense or held by countries like China, which they don't want to publish. So they may be existing, but that is not known. This information is what is publicly known and submitted to top 500.1. So this is the basic thing about we saw that algorithms and top and supercomputers that we have, what power they have. But supercomputers are typically used for solving science and engineering problems. And engineering is nothing but manifestations of what science tells us. So the traditional way of doing science was that you propose a theory. Like Newton said that there is a gravitational force that exists. That's a theory itself. But putting it in theory doesn't make it science unless it is proved through experiment. Like you throw something, anything you throw, it comes back to Earth. That is the experiment you can do. Or somebody proposes that this kind of drug molecule will be good for taking care of this virus that is affecting humanity. Now, how do you do it? You do in a wet lab. First, see how the interaction takes place. You are satisfied. Then you go to animals, create vaccine due to animals, see their behavior. Then you do trials on human beings. And finally, find side effects. All this you do. And then you say that, hey, I can do this repeatedly. Can do this so to the extent repeatedly every time you get the same results. Then you say that this is not fluke, but this is science. This is what we have been doing till computers came in. This is the way Louis Pasteur did it. This is the way Newton did it. This is the way many other Nobel laureates did it. That they proposed the theory through experiments, they proved it, and then we accepted it as a science. However, while they were doing all of this, the underlying fact was what Galileo said a few centuries ago, saying that mathematics is the alphabet with which God has written the universe. So anything that you do, that you see as a science, be it physics, chemistry, astronomy, astrophysics, anything, you will find that mathematics is one that has the algorithm that shows how things are being done, that forms the basis for all of, even in biology, you will use mathematics, you will use statistics to arrive at conclusion, to do things that solve the problems that you have, or draw inferences. So this is the fundamental thing that which suits us, which suits the mathematics. Something which has to do with mathematics is good for computers. Hence, the modern way is do what theory, experiments, but not stop there. Use computation. The last part where we did the experiments, which are purely in wet lab or through physics or through chemical reactions or whatever. Before doing that, before going to experiments, you have an advantage of doing something with computers, which means you can use algorithms, design algorithms that can run on computers. You can think of simulations, you can model something, and then you can use computers to do it. And the greatest example of that was the vaccine of COVID, as mentioned earlier. If we were to use the traditional way, the vaccines we would not have got for a couple of years. I mean, in the past we have seen that vaccines are taking 5 years, 10 years to actually come to the market, and a lot of money is required. However, you can shorten the wet lab experiments. How? You have the possible things. One of the things that they did was what is called as drug repurposing. You have a drug to treat a disease, and there is another disease which have got some similar characteristics with the existing disease, or it has similar characteristics to multiple diseases that we have, and we already have a solution for that disease. Can the potential drugs that are used for treating those existing diseases, can we model them and find out how they treat the virus that is being causing the new disease? That is called as drug repurposing. And one of the things that they did in case of COVID, they listed out such thousands of such drugs. Then each one of them was modeled to see how it docks with the coronavirus. And out of those hundreds, they came out with a dozen that had a potential to be a possible vaccine. So if you were to do thousands of wet lab tests, it would have taken a lot of time. But if you know that out of those 1,000, these 10 or 12 are good candidates, you just do it. And that's how the cycle got faster. And at that time, every country had committed the HPC compute power that they had for this purpose. Even in India, we had Paramsiddhi AI today that was used for doing some drug simulations on Ayurveda molecules. So this is how the computations help us, and that's where we get into a field called computational science, which is of course science and mathematics is the basis of this, and there is a computer science that we saw algorithms, and what I described in the first slide was nothing but computer science. So we get computational science, and that is why this center is named like that, because they deal with applying computers to solve the problems of science. Okay? That is where we get to this concept of computational science, and that is the crux of what we are going to study in the next 3 days and today. Okay? So why do we need HPC? You will find from the humanity perspective, in day-to-day life, we need them for weather forecasting and early warnings, especially cyclones and other things, predicting them. Then improving healthcare, because that is one of the biggest problems that we have, that humanity faces the challenge of different kinds of viruses and other things, which Corona was one of the very sad examples of that. Then in science, we use for developing new electronic structures. We have people from material science who are extensively using computers to design new materials based on the properties that the molecules have. Then just now Professor mentioned about the simulation for the entire universe. What happened? How did we reach this stage? So that is one key thing, that question that humanity faces: how the Earth was born, how the human beings came into existence, how other living creatures came into existence. That is the exploring universe. Then in engineering, this is a very extensively used. Some of you might be aware of products like ANSYS, which do all this kind of modeling and simulation. So you simulate things before you actually manufacture. I will give some examples. Or even for safe structures, like you are building a structure which is in seismic zone rated as grade 2. So what kind of earthquakes on Richter scale would that area be subjected to? So can you simulate, if you design a structure with so much of concrete, having so much of iron and so much of cement, will this be good enough to sustain them? I will give some examples. So taking it further, atmospheric science, that we all know, one of the earliest grand challenge problem for supercomputers has been climate and weather forecasting, to know how the weather is going to be, and that's how even India needed a supercomputer for weather forecasting, and it was denied, and that's how CDEC was born, and I'm here in front of you. So weather forecasting is one of the prime examples as a grand challenge problem for supercomputers. Then air quality monitoring. This is another problem that we are facing now, that the cities are getting congested, and vehicular pollution and other kind of pollutions are affecting air quality. I'm sure you are reading it in newspaper that during this World Cup, no fireworks will be done in Bombay and Delhi, because air quality is already bad there. So we don't want to add more pollution to that. This is one of the challenges of the urban regions. Then earth science, this is for understanding the physical properties of earth and for water resource modeling. Then it also refers to seismic processing, which is used for finding oil and gas. So there are a lot of things that our earth offers. It can be modeled and used for various purposes. Space science I already mentioned. Either you get big data from telescopes and all, which has to be analyzed, or you are trying to simulate some of the things like how stars are born, how dark matter works. All those things can be done using supercomputers. Then another area, very important one for human beings is life science. I already give you example of drug designing. Then genome sequencing. This refers to, you may be aware that every individual has a unique genome sequence. And today when we go to a doctor and say that I am suffering from cold, and you go to doctor and you say I am suffering from cold, he is likely to prescribe the same medicine for both of us. But there is something called as personalized medicine, that there may be 5 ways to treat cold, but which one is best for you can be decided with knowing of the genome sequence. Then protein folding, again that is used for designing of drugs. Similarly, in nuclear science, one is for nuclear power and design of reactors, but another important use is using the right amount of dosage of the appropriate isotope for treating cancer. Then material science, I already mentioned that the nanomaterial design is one of the upcoming field. Like here you have a stent that is going to go in the artery, and what should be its properties so that it doesn't, not only expands the artery but it doesn't allow clogging it again. So those properties can be simulated on computers, and then you can get a better design of a better material. Coming to engineering, in automobiles, it is very frequently used for doing crash simulations. Before computers with enough power came in, the only way was to crash a car. And some of you may be aware of there is an NCAP rating for a car, like 5-star, 4-star, etc. So there is a test that they have to go through, and they put sensors and see how safe the passenger remains when it is subjected to certain forces. Now, one way is you design a car, manufacture it, crash it, and then find out which elements went bad. Okay, this side grip was not good, or this front grille was not good. Then you reinforce it, make another version of the car, again crash it, see that it is okay. That takes time, money, waste of material. However, if you can simulate it, then you can, by simulating itself, you can find out which are the weak structures, reinforce them, manufacture it. Once you manufacture it, maybe 1 or 2 cars can be crashed to validate your design, and then you can bring it in the market. Aerodynamic simulation for any solid that moves through a liquid or fluid like air or gas, or water. Like for example, a submarine, or a missile. How should be the cone? Shape of the cone should be so that opposite forces are minimal. So that can be done through aerodynamic simulation. Similarly, structural analysis I mentioned. Let's say we are building this bridge. It has got static load and dynamic load, and there are external forces like wind forces, maybe earthquakes. So whether this structure is going to be safe when you build it, are there enough reinforcement? Is it stable? All that can be checked before you actually. So these are some of the key areas where the HPC can be used, because these problems have got very large computations to be done, and HPC can be used for doing it. So what we have seen till now is there are things like algorithm, and that needs a lot of computations. So we have supercomputers which has got good compute power, and they are suitable for solving some of these problems. So at any point in time you have a question, do ask them. So any questions about what we covered so far? Yes.
Do you think the computation power we have in country will be available in the computer system after 50 years?
Yeah, 50 is a long time, maybe 5 to 10 years.
5 to 10 years.
Yeah, that's how it happens. But what you can do is this HPL program that I mentioned. HPL program is also available for Android. Android. Somebody has compiled it for Android. So you can go to the Play Store, get it, and run it on your mobile phone, and then use this chart to see if you had this mobile phone 10 years ago or 12 years ago, you would have, if you could go back in time, time travel, those many years and show to this folks, hey, you have the top supercomputer, but I have a mobile phone which is more than that. Okay. So just check that out as an exercise in the evening. Download the HPL, not now, so don't do it now. Now look at what I'm telling. And then in the evening do it and just use this chart. It's available on top 500 org also. So see how much back in time you were required to go to have the fastest supercomputer in the world, same power in your pocket. So 50 is too long. I can say this is 1.33 petaflops. No, 1.33 petaflops, 1033 teraflops. So then maybe in 10 years time, currently it is not one of the top 500. It is in one of the top 50 in India, but not in the world. Any other question?
You said that there is one German logician who said that not all problems can be solved automatically. Sir, is it that is those things not solvable at all, or they are waiting to be proved?
No. So there are two types. One which you can theoretically prove they're insolvable. Actually, and you can read through this article on Scientific American or some other magazine where they have explained how he arrived at that, and it is accepted fact. And actually, the world got surprised when he proposed that theory. Oh, it's like that, scientists, but they acknowledge what he says is right. But it is in theory what he proved. Okay, so there will be some problems that are actually not solvable because he proved it mathematically. Why it is not? So I am not a mathematician, so but those who are from mathematics background will be able to appreciate it. However, as I mentioned, there are some problems for which today algorithm does not exist. So they are that's the one. One of them is what actually a research scholar doing PhD should be interested. Okay. Pardon?
We have a hard problem in algorithm.
Yeah. So yeah, you may know better than me. Okay. So those who are from mathematics background, they may be able to.
In algorithm, we have a hard problem.
Yeah.
Which I checked.
Yeah.
I think all of us know.
Yeah. Some of you would be aware, some of you who are not from mathematics background, I mean, you can possibly during later tell them what it is. So some of them people find a more efficient algorithm, solvable algorithms, but because earlier the computers were of a different kind, they took longer time. Now you have a different type of computers which have got certain additional features. The algorithms become I mean simple example like till maybe 10 years ago or 12 years ago CUDA did not exist, GPU programming did not exist, so we would use only CPUs to run our algorithms. Once CUDA came in, and as I mentioned, it has got certain abilities, people were trying to find that, I mean researchers that okay, these algorithms can better move on CUDA, or this section can be better done on CUDA than CPU. So like this, that also gives rise to a better different kind of algorithms or modified the algorithms to suit the underlying hardware. Anybody else? We'll move ahead with basics of HPC. So the principle on which the supercomputer works essentially is you have to solve a large problem. For small problems, you have your standard computers. They were fine, like sorting algorithms, small data set, your computers were fine. But when you have a large problem, these problems can be divided or broken into smaller ones. That's what we do in our life also, that you want to attack a big problem, you will first say that okay, I will divide it into this. The key lies in the fact that they are such, the smaller ones are such that they can be solved concurrently. This is the important thing. If you are broken down into small problems, but the small problems are such that they are serial in nature, that output of one goes to second, only after second is computed, then only you can go to third. If the steps are like that, then such algorithms are not suited for HPC. You have to have a mechanism or identification of small tasks which are very much independent. I mean, they need not be completely independent, but mostly independent. There can be interaction between them, but there should be some portions which are independent of each other. Okay, a simple thing. Let us say you have 100 numbers and you want to find the biggest number out of those 100 numbers. You can write an algorithm. Just one say that the first number is the biggest. Keep comparing with the remaining 99, and whichever among in those 99 comparison, every time you find a new bigger number, you replace the current bigger number. At the end of it, you will get the maximum among them. Right? So this you can do it for 100 numbers on a computer. Maybe if it's millions, still you can do it on a computer. But if this problem becomes 100 million, 1 billion, 100 billion, then you may take a week or 2 weeks to get to it. But what you can do is, suppose you have 1,000 processors. First processor can divide the whole set of data into as many processors you have. Alright, and give a chunk to each one of them. Now, one processor finding the biggest among those that are given to you has nothing to do with this. This fellow also can do it independently. Third, all 999 can do it independently, and each one of them can report the biggest number they found to the first one. What the first one has to do is just compare the 999 numbers and find the biggest one. So what have you done? You had a large problem to solve, divided it into 999 smaller problems. Each one of them, in this case, is a maybe say ideal case where no interaction was created among the 999, but in real life you may need actual problems that you solve, and then you can say that this is like a master and worker kind of algorithm that you did. There was one master who started, then he spawned the data across, divided it into 999 chunks, gave each chunk to each of the processor, each reported one number, and it found the biggest number. So what you have done is you divide it into smaller problems and then solve them concurrently. So if you can have such a mechanism, if the algorithm that you have, if you can do this, then it is a problem that is suited for supercomputing. Please note that it is not that you have a serial program that is running well on a computer and you take it to the supercomputer and say it will run in half the time and 1/3 the time. No. You have to look it from ground up. This is the supercomputer I have. This is the kind of architecture I have. This is my algorithm. Possibly it is running serially on a computer. Can I make it run on a computer? Or I am thinking of a new algorithm which is inherently parallel in nature, which can suit what we are doing. So that's where, because we have found concurrency, the speed up will come if we can run them concurrently. How can you run them concurrently? Because only then you have multiple processing. Then what you will do is you have additional 999 processors with you. Give the task to additional 999. So having this 1000 processor is important for us in this example. So we have to have an architecture which has got multiple processing elements. Okay? So if you look at the traditional IBM PC, when it was made by IBM in 1981, it had a single CPU. It could run the OS or it could run an application program, and then give you the system. So we are from there we have to graduate to having multiple processing elements. You also have something called as concept called distributed computing. So in this case, the difference lies in the fact that you still have multiple processing elements, but they are typically isolated and heterogeneous in nature. Meaning, consider the situation: you have a lab in your college which has got 50 computers connected using Ethernet LAN, and you can actually use it for this kind of work. Some of you may have heard about this called as SETI, Search for Extraterrestrial Intelligence. So there is a program like that, and what they say is they collect data from the telescopes, and you have to analyze the data. So what they do is they give you a screensaver, and the screensaver downloads certain data, and when your computer is not in use, it will process that data and report the results back to the main server. So this is like distributed computing. Wherever you have compute power, SETI, search for extraterrestrial intelligence. So this is just an example where what they did was they gave a screensaver. These days we don't use screensavers, but earlier you would have seen 5-10 years ago you had some moving objects. What used to happen is at that time you had those screens which were phosphor based, and if the screen is on, it would burn the phosphor. So they would try to reduce the exposure. So at that time this was done. I'm not sure whether it is still in place, but you can also search for something called as BWolf, BEWOULF, BWolf clusters. So they make use of this Linux and Ethernet. So it will not be as a supercomputer as I described, but it can be a distributed computing computer. It's here. Yeah. You can just check the spelling, but you will get it. BEWOULF. Wolf. Maybe I might have made some mistake here. Just check. Google will help you in locating. BWolf cluster. So it is general purpose Linux boxes with gigabit Ethernet. Simple. That what I'm trying to say is people have even this people have made using Raspberry Pi. If you have let's say 16 Raspberry Pi, you can actually use it for learning HPC. It's possible. Because finally, performance is not what we are looking at. We are looking at the environment, which I will explain later. So that is distributed. Just let me know if you want to take some 5-minute break, if it's getting boring or something. So let me know. I'm not keeping track of time. Yeah. So as long as you are finding it okay, I mean it's 1 hour, we are done with 1 hour, but let me know in case you want a quick 5 minutes. Okay, so now what we saw here is the basic principle on which the supercomputers work at the lowest level. It's multiple processing element, a problem that can be divided into multiple subsets, subproblems, each problem or each module or each task assigned to one processor. So there will always, when you write a program that runs on a supercomputer, there will be initial portion that is serial, a portion that is parallel, and finally a portion that is serial. You can very well imagine this, that there is a supervisor in a factory who is dividing the work to multiple workers, and they complete the task. At the end of the day, he takes a stock of that, and the product is that kind of situation you can assume when you have this kind of multiple elements, one of them being the one that starts the process and then all cooperate with it and then finally get done. So this is the basis of it. Now comes the term called as high performance computing. So now where do we, I already explained to you where you use HPC, but what is the underlying principle of HPC is you make parallel processing may acknowledge is the need for HPC, and you will use for running advanced applications. I have already mentioned that for small problems you don't come to HPC. HPC is not a magic pill that you use it with a serial program and it runs fast. No, it's not like that. You have to write programs specifically to run on a high performance computing cluster. So where is it finds its primary use? It finds its primary use where large amount of simulation, modeling, or large amount of data, or a lot of mathematics is involved. Such kind of problems if you have, then use HPC because it is tuned. We said that its power is measured in floating point operations it can do. So it is good at doing large amount of floating point operations very quickly. Okay, so we will use it for applications that has got mathematical calculation, and we acknowledge what Galileo said, and that is also the underlying principle on which supercomputers are designed. And you have certain problems, certain situations which involve a lot of mathematical calculation. HPC is where you should be coming. And we also said that it's not a generic thing where just bring anything and it's fast. No, we said that it uses compute power to execute a certain few applications, and we are trying to extract performance by running it very fast. So if you run it very fast, the supercomputer will become free earlier. You can run the next program like this to make use of. Finally, in common language, when you use the word supercomputer, what it means is that it is a one that performs at the near the currently highest operation. So we already mentioned that supercomputers of today is not going to remain supercomputers of tomorrow, and supercomputers of yesterday are not supercomputers of today. So this, I'm sure you got it very well. So this is important. It's a moving target, and it is a term with which the power will keep changing twice a year as told by top-minded developers. So this is the HPC. So now we have understood the algorithm is the key, convert algorithm into computation, and then you solve it using supercomputers. We also said that parallel processing large number of elements is what is needed for us to achieve that power. So now let us understand like how we have built Param Shakti. What are the components that are there in the Param Shakti? The heart of the Param Shakti, okay, there are various architectures out of which they are basically, if you know Flyn's classification, all of you has studied that, it's of type MIMD, multiple instruction, multiple data. I'm sure you know that SISD, SIMD, MISD, out of that, multiple instruction, multiple data, that's how they work. And there are various underlying architectures out of which a cluster. What is a cluster which I mentioned here? The number of nodes connected using network. Why we use this architecture is because the nodes are themselves very cheap. They are available off the shelf. Otherwise, you have to build a computer from scratch like Gray used to do it. But then today, the most prevalent architecture is clusters. So let us see how we build it. So you need compute nodes. Compute node is whose structure is no different than your laptop. Any computing system in the world, whether it's embedded system or supercomputer, you have these elements: CPU, memory, I/O. All of us know that. So same thing appears here. That this box, I'm sure you can guess. If you have a box like this, a computer like this, same thing like this, it will have same thing. That is CPU, memory, and I/O. But it is slightly different. How we will see. So this is, I will describe what is inside this later, but you can take 10 computers, you can take 100, when you go to Param Shakti, they will tell you how many such compute nodes they have. So as you increase the number of nodes, your power is going to increase. But you want them to, for this you need, here you have gigabit Ethernet, when you have something like this, you have a switching family. So there is a primary interconnect, Paramnet, InfiniBand. These are the ones. What is its characteristics? Its characteristics is that it is a low latency, high bandwidth network. Ethernet is a local area network. This is called as system area network. Ethernet is meant to connect hundreds of nodes, thousands of nodes. Entire, if you look at the campus here, you have fiber optic backbone, and every building has thousands of computers, but each one of them can reach any other one. Give the IP address. So scalability is the primary design criteria of gigabit Ethernet. Here you will find the Param Shakti, entire Param Shakti is in a 2000 square feet room. So none of these cables, they may be more than 10 meters long, whereas Ethernet can go hundreds of meters, and then connect switches, bridges, its entire, let's say, 30 kilometer, 30 square, 30-acre campus can be byte or even more. So here it's a high bandwidth, low latency network which allows communication between this set, and also it allows communication with what is called as a storage, which is the parallel system. So this is the where your data and code resides. It is brought in on this node and this primary interconnect. And why will you call it as a parallel file system? Like suppose in a C, you write a C program. There is one process that opens a file in read-write mode. If you try to open the same file while the first program process is open in read-write mode, it will only allow the other program to open it in read mode only. It will not allow it to open it write mode because it is locked for writing in the first process. However, this file system that we have, it allows multiple processes to access the file in read-write mode, but the way the programmer does is, if this is a complete file and there are 10 processes that are running, we will divide it into 1 to 10 and set the right indices for each of the process. That one process will operate only on this, second process will operate where first process ends. Like that, the programmer has to do, but the parallel file system or the PFS, it will allow this to happen. That is the difference between a normal file system and a parallel file system. Then you must have heard about the SSDs. So how do they differ from magnetic media? What is the basic advantage they have with SSDs?
No moving parts.
Pardon?
No moving parts.
That is one, but speed. I am looking for this answer. Okay. So this is optimized for space, large space, whereas this is optimized for speed. So this will contain large amount of data, out of which this compute node could be using part of it at a given time. That can decide. So if the frequently used data and code is kept in this, it will reach the nodes faster. So that is storage acceleration. Then comes, you would have heard about GPUs. I will give a brief introduction to that later. So they, some of the same nodes, they will contain the GPU card. That means if you have certain algorithm that needs to use GPU, to run it on this node. If your program is old, WRF kind of thing, which is using only compute nodes, to run it on this. Okay. So that is that.
Sir, computer CPUs.
Yes, I will tell you what is inside. Okay. Then of course you have the hierarchical storage management for taking backups and all. You also have one more thing, which is the, if you notice here, the red line is the high bandwidth network, the black line is gigabit Ethernet. So this, every box today you get, typically it contains built-in gigabit Ethernet. So you use it for what is called as system administration. So here you see what are called as boot servers and management nodes. So now every node cannot have a monitor and keyboard. You can't have that. So, but what you can do is, I'm sure you have used things like Telnet or SSH that you are going to use now. So with SSH, so like he mentioned, you will find that there is a room that is dedicated for system administrator. They have big consoles. From there, they can reach any of the nodes, see its health. If there is a problem, the alert will come here. So that is management. So typically, when you start your PC, where does it boot from? Where is the OS coming from on the PC? C drive, hard disk, right? But you also have a provision of loading the OS from the network. There is a setting, you can not for the desktop but servers, you can get the image from network. So the image is kept here. Now, can you tell me what is the advantage of putting not on the hard disk here, but putting on a common hard disk here? For let's there are 100 nodes here. What is the advantage you get? No, it may not be fast because it is coming from network, not from the local. It's coming from outside. But
Security.
Security in what sense?
Like, if the management has the data, then these
See,
computing.
image is coming. See, Typically, you have an image of the OS, let's say Linux, on the hard disk. It loads it in the RAM and then passes control to it. The OS comes up. Instead of that, it is coming from the network. The key here is you have hundreds of nodes. So what is the idea behind having such a thing? More than that, we are talking about management.
Consolidating the data.
No, there is no data here. It's just that the image instead of coming from the hard disk is coming from a network.
Some like some sort of monster node type.
Yeah, it is. But what advantage does this arrangement give us over? Suppose there is a situation where the image is in each of these hard disks. You are close to it, but pardon? No, that's separate. Here we don't use them. For this, for cloud computing, I will use virtual machines. Pardon? So the advantage is that suppose it was here and there is a patch you want to add, something improve the OS or fix a bug that it had. What you have to do is log into each one of these and update it. Instead of that, you change the image at one place and you still have the liberty. Other thing is you can say that all these nodes will load that image, or you can say first from nodes will load the previous image. Next 10 nodes will try the next image. You can configure it the way you want. But you have to change it just here and tell this fellow what is the file name. That's all. Are you getting this? Adding patches. You add the patch here, and just reboot these nodes. What I have been told? They have been told to get the image from the boot server. That is the boot server. So the OS, Linux OS boots gets the image from here rather than their local hard disks. So you can do it very fast, changes, and one place to do it and tell arithmetic broadcast, pull it from this. That is the advantage of this. Similarly, you have a concept called as login nodes. What are they used for? The users are here. This is a compute node, compute cluster. You don't have access to this. Users will log into this. It will be told to you in the hands-on class, which is where you should go and teach. So this is used for compilation. This is used for storing. Running your what you call it as there is something called as SBatch. So Slurm. So you submit the job to the login nodes. Your data is residing on the parallel file system, and there are two types. I will explain that later. There is something like home area and scratch area, and then you say that I want to run my code on 10 nodes. So 10 nodes are allotted. Your program is loaded here from your home area, and the job is. So there is no interactive thing. Okay, how is the job? A job is take the input from this file, process the data, write the output to another file. When the job is executed, email will come to you that your job is over to examine your work.
Sir, it is necessary for login nodes and boot servers to connect.
No, see, this is used purely for management part. The system administrators are what are interested in this. Okay, and the users have got access only to this. They cannot reach any other things here. They are explicitly stated in the job file that you create as to how the remaining element should be used. It is like an example would be that you go to a dry cleaner and you give your job and say that do this on it. You don't have access to anything else. There is a window through which you give your job and then it gives you back your completed task. Or you go to a tailor and give certain things. So in this case, it is through the files that you have. Configuration file, and there is a file through which you give other parameters. Okay, that will be told to you during the hands-on session. Okay, how it is.
The management nodes, when we are using the resources from the login nodes, does the management nodes decide on what?
I will come to that later. The next how it is done.
Sir, is there any particular reason why all the supercomputers use Linux OS rather than any Unix like Mac OS.
Right, I'll cover that in the next. Alright, so this is the complete, like you may not be actually because they will be in a rack, but internally they are divided into this kind of parts that you will see as a part of a visit to the supercomputing facility. Okay, so if this such a complex thing exists for the hardware, it has to be complemented with the software stack. So let us see what are these components. At the lowest level lies the OS. So we use Linux, set the number version can keep changing. So the reason, so it's a Red Hat, same thing as Red Hat, but it is an open source. So you don't have to pay for, you have to maintain it yourself. So the advantage is that it's a, you ask why Linux, right? Why not Windows? So one of the reasons is that it is traditionally all supercomputers have been using Unix for two reasons. One is that you can configure it the way you want. Like here, this Linux that we have, it does not have print services. It does not have other services which are not required. Basic thing like file service and the I/O and bare minimum things that are needed for running the program. Core and OS, core and OS. So you can. One of the reasons is that you can configure it the way you want. What is that you need? You can compile and make an image. That is the first thing. And traditionally, it is known that the security in Unix is much better than other operating systems.
Mac OS is also Unix.
Correct. But do you get it free? Don't get.
Cost is
See, you can get into that debate that I want to use Mac OS. One can do it. One can make a custom using Mac OS. But what happens is the community support and the popularity is what drives your decision. That there are so many things that will be available off the shelf free for you if you use this. But if you want to do it on Mac, perfectly fine. People have done it using Windows. There used to be a time when Windows was the because NTFS and when the Windows Server came in, they made an attempt to make it available for HPC application. But what happened was the community was not ready to move over what has been traditionally followed, and it is much easier because in case of issues or something, the whole community is supporting you. Here you are on your own, but you could be the pioneer.
Sir, coming back to this question, I think Mac OS does not allow us to change the API file system from the basic level.
So those things will come later, but one can see when you have an OS and a networking stack, you are ready to implement this. Okay, so that is the basic thing that is needed. But whatever is not present that you need, you have to develop it yourself. That is the thing.
Another question that why CentOS? Why not another distribution of Linux?
Anything you can use Fedora, you can use. So what I'm saying is this is what we have made it. We have decided on using this. So again, I may not be privy to the decision where out of these why this was chosen, but there would be some of the compelling reasons like how popular it is, what is the community support for this, and many other things that would have because at a given point in time there may be something like 50 or 60 flavors of Unix that are available in the market. Okay, but I can check that out. My colleagues who did this will be able to tell me why CentOS is chosen. It could be popularity and support.
So, with CentOS and Red Hat Enterprise Linux, I think there is a good support to evolving HPC. A new system comes up, a new switching infrastructure comes up. The community involved in the development of these two parts of Linux, not wrong. So they are quite vibrant and they immediately provide support for, let's say, a new InfiniBand switch version has come up. So these are primarily the two communities who will immediately provide us support at the device level for such.
And even because what happens is at some point in time, it is a vicious circle. Like for example, you take USB thumb drives. I mean, maybe you have not used it 10 years ago or 15 years ago when they came. they were in KBs. Okay. But at that time, hard floppy disk, 1.44 inch floppy disk, and they both of them were in use. But over a period of time, it became so popular and also driven by the cost of memories. The price came down, so people started using more. So now that has become a de facto standard. USB thumb tries to use it. So like this, be it for OS, be it for any other product, once they become popular and there is a sort of some trigger point where they start becoming popular, so price comes down, they start becoming popular like that. So this is the one. So to add to what we said, let's say InfiniBand makes a new car, they will provide drivers by default for CentOS. They may not give it for all 20 others, or they will give it for 5 of them, out of which CentOS being the most one. So that is, I think, would be a risk. So at the lowest level is the OS. Then comes the middleware. So in this, there are 3 things. First is the monitoring. So this tells, like somebody asked this question, so there is a monitoring tool, a client which is running on each of the nodes, and there is a server. The server gets to know these are some of the things, Candia, Nagois, XTMod, these are some of the standard cluster monitoring tools which tell what a particular node is doing, whether it is up and running, is it been assigned to one of the jobs. When the job finishes, the cluster monitoring tool gets to know that now this is. This will work with the provisioning tool like OpenHPC. What does the provisioning tool do? It takes help of the monitoring tool to maintain a map of which nodes are free and which nodes are occupied at any given point in time in real time. Who will use this? This will be used by Slurm. The user interface is to Slurm. What is Slurm? It will manage the resources to the provisioning tool and it will schedule that. As a user, what will you say? I want to run this program using 10 nodes. That's what you will tell. You don't know which 10 nodes. Who will do that for you? Slurm will do that for you. How will it do it? It will go to provisioning tool. The moment your job is fired, it will go to provisioning tool and ask, hey, 10 nodes are available? Yes. These are the ones which are available and you can use them. No, 10 are not available, 8 are available. So wait. What coming in the and the job is.
This is held in boot servers.
No, so don't worry about that. Okay, it is available in the cluster. We will not get into those details, otherwise it will complicate the matter. So I cannot say.
Sir, you talk about nodes. So exact definition of nodes is a CPU with some.
Correct. So I will come to that. You are typically asking. I have, since I have not introduced that word, I am using the word node because the granularity is at the core level. Cores, how many cores you want?
So
Because
the system supposed to have 4 cores or 8 cores in a single system, a personal computer. So can I consider it with 8 nodes or a single node?
so node is one, in a computer it is one. I'll just wait for some time. I will explain that.
Sir, I think Candia is a web-based cluster monitoring system, right? Like if I put the IP of the cluster, well, it will show the.
So don't worry about that part. Okay, I am explaining you only to know what is the structure. As a user, you are using Slurm. SBatch is the command. Okay. So if you are a system administrator and you want to get into that, details of this, how it is done, how it is administered, that's a separate set of training that you have to undergo. So, and most importantly, I am not equipped to answer that. I will not give you wrong answers. I am not, I will say I don't know. And the reason why it is not covered. Alright. So this is the middleware. Then comes the programming tools which the user uses. So first one is there are some libraries like MPI will be told to you. So MPI is a library that you have to use. Okay, so there are various libraries that are available at this level, and because Param Shakti is based on Intel architecture, you have one complete package called as Intel Cluster Studio, which contains the MPI libraries. How MPI works and all, it will be told you, so I will not at this point get into that. Then there are development tools. What is a development tool? Compiler. Then you have the debugger. Then you have a linker, loader, all these things. So in case of a normal program, you have a .c program. You run a batch, first it compiles, generates the object code, then it links, gives the loader, loads in the memory, and your job is done. Here, you will get an output file, which you will have to submit it to Slurm. And along with that, you have to tell how many nodes you want. At this point, I am saying node. Finally, it will get translated into how many cores you want. So once your program is running, you have to use certain things like debuggers. So there is a parallel debugger included in this. There is also a tool which does performance monitoring. That how much time is your program taking, which module is taking more time. So all that is anyway, that's an advanced programming practice. In this workshop, you will only learn to write a parallel program and make it run. Maybe try to see whether it is scaling. If we increase the number of nodes, does the time reduce? Those kind of things is what you will learn. But finally, when you write a big software package, you are concerned about its efficiency, its time that it takes to. So I hope the stack is clear. As far as you are concerned, you will be using the Cluster Studio or part of it, and thus, so these are the user interfaces which the user uses to write a code and run it. Moving ahead, what we saw was we have processors in the box nodes. In the box or the node, there is memory also. External to the box, we have the system area networks. Some of the nodes have got accelerator or processor, the co-processors like GPUs. We have entire storage subsystem which uses the parallel file system. And in fact, here there are two things that we saw. I did mention Lustre is the parallel file system, which is a scratch file system. The intermediate results are written here. I mentioned about this parallel file system, that is Lustre, and NFS is your home area. When you log in, you get a home area where your code, data all reside. From there, when the program is executing on the machine, it is using Lustre file system because you want a parallel I/O. Once the parallel part is over, you will again the result will be stored in the NFS home. So that is the part which is the parallel file system. On top of that is the software, OS compilers. Then if you are writing parallel codes, MPI you will use, or multi-threaded or a hybrid, all this will be told to you. And finally, you will use debuggers in case you don't get the right results, or you can monitor the performance, analyze it, and so this is the complete thing that you see as a part of a supercomputer. So now we had questions about what is inside that box. Okay, so this is an example of a supercomputing system. So the picture may not be very clear, but here there is a rack, and rack has got 1, 2, 3, 4, 9 nodes. And there are 288 nodes in this, which is Param UART 2X CDAC today, the old system. This picture I have shown. So you will see some cables also here. So these are the network cables, and all 288 nodes in this are connected to each other. So now, what is this white box? It is actually a rack server like this. And inside 1, 2, 3, 4, 9, whatever. So typically, this is the height is what is called as 42U. Part of it is for networks, part of it is for compute node. The compute node will look like this. So you can imagine this one box goes here, and 9, 10, some certain number of boxes inside this. At the back side of it, there will be cables. What you see here are the hard disks that will be available. So it is just a box in which inside there is something which I will show you the next slide. So that is a motherboard. Many of you would have seen this. If you open a box, this box will also see something like this. However, this has 2 CPUs, and so many blue color are the memory slots, and white ones are the IO. So the InfiniBand or permanent card will go here. The memories will go here. So you can have 64 GB, 128 GB, 6 GB, that kind of memory. And each one of them takes 1 CPU. So the most commonly used node has got 2 sockets, which means it can take 2 physical CPUs. Xeon. So typically we will use the best server class processor for this. How do we define the best server class processor? It has got good frequency of operation. It has got good number of cores. So today, if you take an Intel CPU, a reasonably good Intel CPU of Xeon class, it will have 24 cores or 32 cores. If you take AMD processor, it will have 64 cores that are available. So if you take AMD processor here, your node will have 128 cores. So one box, 128 cores. If I want to use up to 128 cores, I will typically the slump will allocate 1. If I want 1000 cores, I may get 5 cores. So the OS will allow each core to be used for a particular.
So, according to the architecture, each core having one daily.
Yeah, I will come to that. What is inside one, I will also tell.
You put distribution of network parallel.
So each node will have one permanent card, and there will be a switch which will connect, let's say, 100 such nodes. So theoretically, data from memory of one node can be transferred to the memory of another node through this.
Each of these CPU uses different OS.
No, they see the OS is running on the entire motherboard. Okay, OS image is same for the entire motherboard. Okay, and the OS will control all 64, 128, whatever number of total cores are here. And typically OS will run on one of the cores, and the remaining cores will be available for use in the pool. So that architecture I will not get into.
Sir, we have the CPU cores, we have the 2 sockets for the CPU cores available.
CPU cores are inside this.
Sir, if a system has a CPU.
So GPU card will go here.
Okay, so the entire thing is one.
Yeah, this one physically, this is one in a box like this. This box contains a motherboard. It can contain permanent InfiniBand card, a GPU card.
You showed that map of memory, GPUs, CPUs, control units, and login nodes. Everything is.
This is inside one box.
There are many boxes like these.
Correct. So this is inside. What I showed is inside this and this. This will not have GPUs. This will have GPUs. This is this box that I mentioned.
So the memory is in parallel files.
No, that is hard. That is not memory. That is your secondary storage. Memory is here inside this. So if a code has to run, it can operate on the data which is here. If it's here, it has to be first brought in, or it can be brought in from here to here. But if you want to add 2 numbers, the numbers have to reside in this memory.
So we load files from parallel file system to computer.
So parallel files, see, you load the files or data from the NFS. This is your home area. When it is generating intermediate data, running the code, it will go into the parallel files. And final results are again written into NFS. So your C drive or /dev/ something, that is this NFS. So scratch is not visible to the user. It is you have MPI IO or something like that while running the code, you will be programming directly. So now let's see how the parallelism comes in at various levels. Professor Day, how much time do I have? You can has Pavitra come? I have to carry on till he comes. That is one, and I should not be including it in Pralay stop. Okay. Okay, I thought it is. I got. So I want to also ask Pralay how much time I can take.
We are overshooting by about
Already. So and he can continue after lunch also.
Yeah. So there's no.
And you should not insist that you go home at 6. Okay. That is why you have been given a place to stay in the campus. Okay. Food, breakfast, everything is taken care so that you can put 70 hours in 4 days. 5 days.
So after your session, we have a
So what? See, I have two options. I can rush through the slides and complete in time, or I can go at my pace, or rather pace of your understanding. So if the tea or something is ready and they want a break, you can definitely take that. I can continue now. Check that out. I see human brain. It's proved that it cannot take more than 1 hour of teaching. So and this is all new for them. So I will not insist that I tell what I know. I would rather insist on taking as much they can take. So I am at a higher potential. You are at
We can take a 10-minute people.
yeah. So after that I will come to this. Okay. So you have to somebody has to tell the online. So we can pause the recording or something. You can pause it later.
So we'll take a 10-minute tea break. He is just outside there. Okay. So he is FPA from that.
And you can tell me if you are getting bored or something, then I can wind up faster.
Okay, so we break for tea. Please be back in